Alrighty, let's do this. Alright, another hard one. Like end of the month, I think they tend to do more hards. Apply operations to maximize score. You're getting an array nums of n positive integers and integer k. Initially, you start with a score of 1. You have to maximize your score by applying operations at most k times. Okay, so you can do k operations. Choose any non-empty subarray between index L and R that you haven't previously chosen. Choose an element x within that subarray with the highest prime score if multiple such exists. If multiple elements such exist, choose the one with the smallest index. So the first highest prime score. Multiply your score by x. Choose an element. Multiply the prime score by x. You initially start with a score of 1. Okay. Here, nums from L to R denotes a subarray of nums starting from index L and index R inclusive. The prime score of an integer x is equal to the number of distinct prime factors of x. For example, the prime score of 300 is 3. Okay, so the prime factorization of something, how many prime factors there are, is the prime score. Return the maximum prime score after applying at most k operations. And it could be a large number. So we'll say mod constant is 10 to the 9th plus 7. So you have nums, you have two subarrays here, or you have 2 operations you can do. I'm not sure why you'd ever do less than 2 if you're trying to maximize this. The nums are all positive. So here you can divide into the subarray that is, I don't know, 8.3 and 9.3.8, something like that. To get a score of 81, we can apply the following operations. Choose a subarray nums 2 to 2. Nums of 2 is the only element in this subarray, so 9. Hence we multiply the score of nums of 2. Hence we multiply the score by nums of 2, which is 9. Choose the element with the highest prime score. Okay, so because 9 has 2 factors, 2 prime factors, 3 and 3, if we choose just that subarray, then we can just have 9. If we had something with 9, 3, and 8 within it, then the 8 would have 3 factors, 2, 2, 2, and then that would have been a higher prime score, so we had to choose a smaller number than 9. Okay, so that's one subarray, 9, and then we can choose another subarray. Choose subarrays 2 to 3. Okay, so the subarrays can be overlapping, but they have to be distinct. So you don't have to use like 9 and then like you can reuse that 9. Interesting. And for the second one here, we can choose 3 subarrays. So 19 has 1 prime factor. 19. 12 has 2, 2, 3. 14 has 7, 2. 6 has 2, 3. 10 has 2, 5. And 18 has 2, 3, 3. So I'm guessing you do like 19, 18, and 10, 18. Yeah, 19. And then just the 18. And then and then choose the subarray 2 to 3. 0, 1, 2 to 3, 14 and 6. Why didn't you choose 10 and 18? Nums2 and nums3 have prime score of 2, but nums2 is smaller since we multiply the score by nums2. If you do 10, 18, it's 2 times 5, 10, and 2 times 3 times 3 for 18, no? Prime score is equal to the number of distinct prime factors. I can't choose 4, 5. Prime score of 10. Choose a non-empty subarray. Choose the element X with the highest prime score. 10 should have a prime score of 10 is 2 times 5. 18 is 2 times 3 times 3. If multiple elements such exist, choose the one with the smallest index. Like 10, 18, you can get 18 again. Or even 6, 10, 18, you can get 18 again. Choose subarray 5. Nums5 is the only element in this, hence we multiply the score by 5. Oh, is it the number of distinct prime factors? Oh, it's not the number of prime factors, distinct prime factors. Okay, so 18 has 2 and 3, 10 has 2 and 5, 10 goes first. So, okay. So, for each, so I think we first need to identify how many prime factors are in each element. So let's start with that, because it doesn't really matter. It doesn't really matter what the prime factors are. It's just how many there are, or how many distinct ones there are. All right. So let's go. Prime counts is going to be an empty array for each value in the nums. I'm going to find get prime count or some value. I can't remember what the actual fastest way to get primes from a number is. Is it just a for loop? And then fastest way to get primes from num. So you have create a Boolean list, mark non-primes, extract primes. All right, I'm just gonna guess this is an arrow. I don't know how to pronounce that person's name. what is this thing doing? So you have a limit where the limit is the highest number that you probably are looking for. And you're keeping track of like the primes that you already found. So first numbers, prime of 0. If the number 0 or 1 is not prime. And then for every number 2 and larger. Okay, whatever. I'm gonna copy paste. Okay, so does this work for me? This is just getting whether or not something is prime. Oh yeah, okay. This give me a list of the primes, but I just need the count, so I can just modify that. So what is this doing here? For every p in the range of the number to the limit, if that number is prime, then how big is the limit here? The values in this array are from 1 to like 10,000. Okay, so I guess that's not too large. I can probably do this once. But you don't really need to do this multiple times. Like this first calculation, primes. There should be some way to store the information. There should be some way to store the information, I feel. Alright, I'm gonna consider this to be something I need to fix at some point, but now let's say the limit is some number, and to get the number of primes, I'm just going to return the length of this list. Alright, I'll just say prime function here. Okay, so for every value in my nums, I need, wait. Yeah, so these are the distinct primes, so the length of primes. I'm going to say the prime counts is going to append the prime function of this value. And then I'll just do a small sanity check here, print out my prime counts, and return 0. Oh, whoops. Is the, yeah, I tabbed that wrong. So I think that's tabbed right now. Okay. That didn't seem to have. Ooh. Yeah, I did not. What is this thing doing actually? What is this thing actually calculating? 8, 2, 3, 5, 7. What is this thing calculating? Oh, it's calculating the limit. Oh, it's the highest, it's the number of primes below that value. Fuck. That's not what I want. Oh, a question from the audience. Why choose 18 next in example 2? I'm not sure if this person is still here. I choose 18. Next example is 2. Oh, I think that was asking about my confusion, right? It's choosing. Oh, you're here. So it's choosing 18 because the because both 18 and 10 have the same number of distinct primes, 2 and 5 for 10 and 2 and 3 for 18. So it can't choose a second 18. I think that's your question. Like 19 would definitely be one of them. 18 by itself would be another one. And then like if it chooses 10, 18, it'll actually get 10 as the prime score of that subarray. If that makes sense. Well, let me know if that's still confusing. All right. So the limit here just doesn't work as the number way to count it. So I think. All right. All right. I'm just gonna do my own function here. Prime, prime, get prime count for some value, and then if the so I'll just iterate through the smallest to the largest value. Gosh, I know I did this in a previous coding thing, and that was pretty darn quick. Just using like a for loop that went through fastest way to get primes, prime factors of a number. Is that going through the for loop and going through? Here's the most efficient way to get prime factors. Go through. It was faster than this, I think. All right, let's go. Let's do that. One of the things about doing very common type algorithms is the difference between what you might code as a general way of, or you or I might code as a general way of doing it, can be far away from the optimal way of doing it in terms of like super efficient how the language or the compiler would approach it. So try and get the most common ways of, like for very common things like getting prime factors like this, I try to rely on other people. So this is going to be the prime factors, and I'm just gonna, I don't actually need to append the count, I just need to return the count. So factors, I just need the factor count, and I just need to add to the count, and if n is greater than 1, factors append n. What does that mean? So if the number is bigger than 1, I'll always include the number. Sure. I think that just means the count starts at 1. And I return the counts. Alright, so let's go ahead and just see if that works now. So prime factors. Okay. I must have screwed something up here. For factors 2, wall factor. Yeah, I think that's what I'm going for. Okay, so I think here I screwed up. Oh, I'm passing in the pending the function itself. Prime factors of this value. Return the count. Not counts. Okay. Still not quite correct. So the count starts with 1, the divisor is 2. If the divisor is less than the number, or the divisor squared is less than the number, and is divisible into the number, increase. This is, it's dividing out that number. It needs to divide out that number multiple times. So while I think this should be if it's divisible, then increase the count of the number of prime factors, and then while it's divisible, then divide out that number. Yeah, I think that's better. Actually, the count should start with 0, I want to say. Okay, so 8 has 1 prime factor, 3 has 0 prime factors. That's not quite right. So why doesn't it? So if you have, I think maybe I should have included the last one. If the number is still greater than 1. Yeah, I think if it's a prime number, it doesn't do this correctly. If the number is greater than equal to 1, number is greater than 1 still, then count plus equals 1. Okay, that's correct. 1 prime factor, 1, 1, 1, 1. And then 19 has 1, 12 has 2, 14 has 2, 6 has 2, 10 has 2, and 18 has 2. Alright, finally got there. Don't think I need this. Let's go and just move it down here. Okay, so once we have the number of once we have the number of distinct prime factors, this should be so you really want to use as many times as possible a prime score subarray, or if you have a very high prime score, if you have a very high number, you want to use that number as much as possible as long as the prime score of it is bigger than the numbers surrounding it, or if it's before those, bigger or equal to, or before, and if it's tied, then it's before those other numbers. So I think this feels like a heap. where it's a heap. Can you use, okay, let's just think of this. Can you use a sliding window? No, I don't think you can use a sliding window here. Like, it doesn't feel right because sliding windows generally don't have overlap. You could have overlaps in sliding windows. It's still possible. So if you got a sliding window, the number of times you do it is seems like it'd be hard for a sliding window to capture. So if you just get k elements, or you got k operations, and you use the highest prime score, highest value, and try to work with that in as many arrays as possible, like k arrays. Like let's say it was 19 and you're trying to get 19 in a bunch of arrays. The other arrays would have to be extending before or extending after if it has the same prime score, or extending before if it had a smaller prime score. And then extending after if it has a bigger it has an equal prime score. Okay, that feels like a heap. So you look at the, does it feel like a heap? You look at the elements largest to smallest, and for each element you use it as many times as possible. So 19, I can use this once because, well, I can always use it once if you just take that as a subarray, and you try to extend it later on and see how many subarrays you can get later on, depending on what the subscore of those are, or what the prime score of those subarrays are, and you extend it in front as much as possible. And then you keep on doing that for every smaller value in your array. Okay, I think that works. So how to do this? I think it would be you can't really sort. Can you sort? Okay, I'm going to do this kind of the brain dead way, and then there's going to be some optimizations, but I'm going to have a sorted array with the index information. So I'll say array is equal to, for every index, for every index in range of n, then I'll just say array is equal to array.append the tuple that is the score and the index. I'm pretty sure there's a much more efficient way here. And then I'll sort the array, and I'm going to say for k, for index in range of k. So I'm going to try to figure out what the, no, this is not right. So while, say that we have a count, while the count is less than k, actually, no, I guess I can use index for going through the actual this actual array. So for index in range of n again. So for each index, I'm going to have the value at the index, and then I'm going to look at the biggest or the most subarrays I can use with that value. So this is going to be, I need to reverse key is equals, or reverse equals true here. So from the biggest value, so I can say while okay, let's just keep, so I'm thinking of sliding window. So the left side of the sliding window is going to be the index that this is at. So, or let's say value and value index is going to be the array at this index. And then the left side of the window is going to be the value index. And the right side is going to be also value index. This is inclusive. So you should be able to extend, you're going to try to extend as far left and right as possible. And each time you extend, should you start by extending leftwards or rightwards? I think you start by extending leftwards. So let's say the 19 was like in the middle of nowhere, or like the 9 here. You start by extending leftwards as long as this value has a bigger prime score than the one before it. So while left is greater than or equal to 0 and the prime counts, which is equal to the prime score of this index, is, should I start with value index minus 1? Or value index minus, and the prime counts of this, of the left side is smaller than the prime counts of this value, then the max score should be increased by this or multiplied by this. What's the calculation here? Max score should be multiplied by it. So let's say the answer is 1 originally. So the answer is going to be multiplied by the current value. Else it stops. That's as far as it goes. Now the issue is the number of subarrays that you can do, or at least, well, value answer equals answer times value and then mod it. The issue I'm thinking of is, let's say you had a huge prime number. Let's say it's like, or a huge number with a lot of prime score. Let's say the number is, I don't know, it's like a huge number. You can extend it leftwards. Let's say the numbers leftwards are these two numbers. And you can extend it rightwards. But the number of times you extend it leftwards will also increase the number of subarrays that you can get when you extend it rightwards. So for instance, if I had just this number extended leftwards 2 times, then when I extend it rightwards, I can get this subarray, and then I can get this subarray, and I can get this subarray. So extending rightward by 1 is not the same thing as extending leftward by 1. You can do the reverse logics too. If you do the rightward first, then extending rightwards, and then figuring out how rightwards it is for each of those extensions, the leftward subarray can increase. So I think there's going to be some math here to determine how many times I can do this. So so this is 1, 2, 3, and then from here this is also 3, and then from here this is 4. Like this is 1, 2, 3, and this is 1. No. Okay, so it's just 3 each time. It needs to be, okay, so the difference between like the value index and the left index is going to be a constant number that each time you do the right side increase, that's the number of subarrays that you do. Okay, so this part is, I think, fine-ish, and then while right is less than n and prime counts of the right side, this should be left minus equals 1. Never keep on screwing up on the while loops versus for loops, forgetting to do the update. While prime counts of the right side can be less than or equal to prime counts of the value index, then right plus equals 1, and answer is equal to answer times the value some number of times, where that number times is the value index minus left index. So initially left is going to be 1 less than the value index. So if you do the subtraction, it's the actual number. So yeah, so value index minus left and mod. Alright, I think that looks okay-ish. Okay, actually, it's not quite okay. You need to actually keep track of your number of times that you've done this. So that'd be the count, right? So this would be count plus equals 1, and this would be count plus equals 1, and then if the count is equal to k, then return the answer. Again, if count equals k, return answer. And I think this should end inside that loop. I don't think this loop goes infinite. Use a monotonic stack to find the next clear element. Give me 1 second. Let me try to finish this thought. Line 54. And the score, this should be the value, should be the value in the nums array. value in the nums array. Wrong answer. Well, it passed a lot of cases before giving the wrong answer here. Let me print out what the prime counts are for this one. Three, 4, 4. All right. Okay. So your comment is use monotonic stack to find the next greater element, the greater prime score for each element in nums. To find the next greater element. I don't think that works. Because you're really trying to maximize your usage of k, and I think it's faster to just go to the biggest values in your array and use that value in as many subarrays as possible before moving on to the next one. And if you do a monotonic stack, what might end up happening is, like, for each value that you hit as you iterate through the array, you're maximizing that value, but that value could be not part of the ending kind of group of k. Like, it would be you're trying to optimize for stuff that you don't know is the best at the end. I mean, unless you can kind of give a more detail into that comment. So 3, 3, 4, 4 here. So it should be using this thing once, and then it should be using k is 6. So it should be using this 22,000, 14,000. It's just so you're using 22,000 once, and then 22,000 again for this subarray. Actually, should be using 22,000 pretty much all the. No, be 22,000 once, and then 14,000. 14,000. Oh. And then 14,000 and 22,000. Nice. I think the issue here is I only use 14,000. Okay. Instead of using count, I'm going to actually do the say my let's say my k values. Let me go ahead and just clarify. So count. Oh, what am I doing? Okay. This is wrong. This is wrong. My count should be increasing by the number of times I actually do this here. Value index minus. Can't even do that because that could go over k. Okay, so I need to slow down my rule here. So while right is less than left, or right is less than n, and prime counts right is smaller than or equal to that, I think I still see another issue that I'm coming across, but am I? Okay. So here it's going to be for I in range of value index minus left, answer is equal to answer times value mod, and then count increases. Okay. And then increase the right side by 1. And yeah. Parentheses is off. Alright, that wrong answer case is now right. Did I run it? Taking a long time. Okay. Okay, 1, 7. So what are the prime counts here? So prime counts here is 0 primes, 1 prime, 1, 0, and 1. Okay, that's correct. So it's doing this 14 times. So it should be using 11 1 time, 2 times. It should be using 11. So it can't go before 11. So it should be using 11 once, twice, 3 times. And then it should be using 7 once and twice. So it should start with using 7 by itself, and then another. So it should use once, twice. Oh god. What am I doing? So if it's 1, 7, 11, 1, 5, the first time it should be using 11, and then it should use 11, 1. It can't go leftwards, so it's using 11, 1, 5. And then it should use 7, and then going leftwards it can use the 1, 7, and then going rightwards it should use 1, 7, 1, 7, 11, 1, 7, 11, 1, 1, 7, 11, 1, 5. How many things is that? That's 1, 2, 3, 4, 5, 6, 7, 8, 9. Wait. 3, 6, 8. So that's 8. 2, 3, 4. Alright, and then it should be using 5, and then it should be using 1, 5. Oh, wait. This is not right. So the 7, 1, 7, and then 1, 7, 11. It should be using multiple times. So 1, 7, 11, and also 6 and 7 is this. 7, 11. And then when it does the 1, 7, 11, 1, that should be a couple more. 1, 7, 11, 1, and like 7, 11, 1. And then for the next one, when it uses 5, it does 1, 7, 11, 1, 5, and 7, 11, 1, 5. 12, 13, 14. These ones it has to use 5. So 5, 1, 5. I guess it uses a 1 for the last one. I don't see any other elements besides 1 for the last grouping. 11, 11, 1, 11, 1, 5, that's 3. 7, 1, 7, that's 2. 7, 11, 1, 7, 11, that's another 2. 7, 11, 1, and 1, 7, 11, that's another 2. Yeah. Okay. So I'm just going to verify that this is what it actually is considering. Let me print out the actual arrays. So for each time it does a count, I'm going to do the print of the subarray. So the array from left index to the left index plus to the value index plus 1, I think. Or no, it's going to be left plus 1 to the value index plus 1. I think that's the left side. This doesn't go out of bounds. Not exactly what I was imagining. 11. What is going on here? Not even doing it for these ones. So it's doing it for that one correctly. Am I using the right array? I'm using the wrong array. Alright, so this one 1, 7 nums from the left index to the value index plus 1. Oh, I'm doing this after I do the decrement for the left hand side. Okay. That's still incorrect. So the left index should be 11. While left is less than, okay, let's, oh. What's on here? Why isn't it processing 11 first? Okay, so the sorted biggest values is 11 and then 7, 5, 1, 1. So first up is 11. So the value should be 11. while that value, while the left side is, so we have value index is going to be 1, or value index minus 1 is going to be 1, and right side index is going to be 2, while 1 is greater than 0, and prime counts of 1, which is 1, is less than, okay, so it doesn't do this at all for the first one. It doesn't do this at all for the first one. How is it doing it correctly for any other ones? This is a major bug in the code. Alright, so while left is greater than or equal to right, prime counts of left is less than prime counts of right. So I think maybe I should extend it leftwards as much as possible, and I guess maybe the right side is where it does at least once. So if it doesn't extend it to the left side, the left is left at the value index. Okay, yeah. And if it does extend it to the right side, the right side starts at where value index is, so the right side, okay, so the left side should be, yeah, the left side should end up where it's the earliest. The left side should end up where it's the earliest. Do you need to extend it on the right side at all? Okay, I think this is fine actually. For each right side value, I'm going to say print the nums at the left plus 1. No, it's actually at the left to the right. Or right plus 1. So it doesn't show the 11. Okay. Processing value. So it's processing 11. So it should be doing 11. It should not be doing 711. I think maybe this should be left plus 1. So it's 11, 11, 1, 5, 11, 1, 11, 1, 5. Those are the three. And then 7, 1, 7. And then it's doing two 1, 7s. Let's see, this is going to be the left loop. And let's say this is the right loop. So on the right loop is actually when one actually does the 1 by itself. Is that how I want it to go? Guess that could work. 11, 11, 1, 11, 1, 5. And then for the 7, left loop should be showing left rather than left plus 1. Alright, the left loop for the 7 should be 1, 7. And the right loop should be... That doesn't seem right. The right loop should be like... Ooh. There's a duplicate 1, 7. I think 1, 7, 1, 7, 11 twice. So if I go left loop and the left loop goes leftwards but doesn't include the same value, doesn't include the self value. Oof, there's just a bug in the number counts here. Because it should be 7. I'm thinking the left loop should be the one that counts the self value. But maybe it's easier for it to not count the self value. So you go leftwards without counting the self. And then you go rightwards counting the self. So if you go leftwards without counting the self, which is currently what's happening, when you count the self going rightwards, then you should be doing, the math should be different here. 1, 7, okay. I think I just need to fix this so that it actually does what logically I'm thinking of. So the first thing is you always include yourself. So I'm going to say answer equals answer times value mod, and then count plus equals 1, and if count equals k, return answer. This probably is redundant, but or this probably could be more elegant and within some loop. It just looks like a fence post issue, but I'm just going to try to work this. So it's doing it without, it's doing the self, and then it goes leftwards, and therefore the leftwards shouldn't include the self at that point. So as it goes leftwards, it's the index that is as the index that goes to is starting with the index before the current index. But that shouldn't be the case. Shoot. So left should end up being in the last spot that doesn't work. And you assume that the last spot that doesn't work is the spot before the current value. Okay. And as the spot does work, then you increment. Okay, you increase the thing. Sure. And so you end up being here, and you end up doing the right side, and where the right side, I think the right side is just doing too many loops. Like it should be value index minus left minus 1. Alright, that broke things up. Okay. So processing 11 doesn't process it at all. So whether we should be doing 3 11s, it's doing 1 11 automatically here. And then it should be doing print left index and top index. So after processing 11, the left index is at 1, which is where it should be, and the right index is at 2, which is where the value index is. Okay, yeah. And then while right is less than n, and prime counts at right is less than or equal to prime counts. So it would be doing itself, no? But you're doing value index minus left minus 1. So value index minus left minus 1 is going to be 0. Okay, that's fine. And then right plus equals 1. So right should be at 2 at that point. 3 at that point. And then 3 is less than 5. Prime counts at 3 is less than prime counts at the value index. Sure. Is it not less than? This thing is not doing the prime counts correctly. Value index is 2. Right side should be 3. So 1 is bigger than 0. This thing is constant. That's constant is 1. That should be bigger than 1 always. Fuck. I see. So this thing should in fact be minus 1 here. Or not minus 1, just right. Value index minus left. So that does need to be 1. that does need to be 1. Okay, so given that now I'm gonna, so that would make it so that if the self is already included, god damn it. Okay. So if you have 11 and you're extending it to the right by 1, then it would be you have 11, you're extending it to the right by 1. You get 11, 1, and 5. And that's your right loops. But the 11 is where you're including yourself. Left loop here is 1, 7, and the right loop is another 1, 7, and one 7. Why doesn't this? Sure. Oh my god. The struggle. I'm about to tear this thing apart. So maybe I should be going rightwards. Maybe that'll just clear up that confusion rather than leftwards first. Rightwards and leftwards are equivalent. Okay, I'm just gonna. So let's go rightwards here. So the value index, the left side is going to be the earliest start, that is, I'm not sure what the leftward side is. The rightward side is going to be the value index. While the right is less than n and the prime counts of the right side is greater than or equal to the prime counts of the value index, then it's going to keep on extending. So it's going to be answer is equal to answer times the value mod, increase the count is to k, return the answer. So each time you do that, that increases by 1. Sure. And now, let's say there is some, let's say the size of the thing is set here. So right minus value index plus 1. So it's always going to do itself here. So it should end up being just right minus value index. And then I think the left side should start with the one before it. Left equals value index minus 1, while left is greater than or equal to 0, and prime counts of left is smaller than prime counts at the value index. Then for each time you have it leftwards, you're going to go to the size. So for iron range of size, increment, forgot the increment here. Answer equals answer times value mod count plus equals 1, if count equals k, return the answer, and then decrement left. And then return, well, that should be it. Okay. Hopefully this refresh is just working. Indent error on line 83. Oh, sweet Jesus. Input time limit exceeded. All right, close, I think. That's a lot of numbers. So let me get rid of the. I wonder if it's. I wonder if it's too slow on the prime factors deal. Because it is going through every value and recalculating the prime factors of this value. So let me just do a quick check here. Counter of the numbers here, print that counter. Okay, let's see if there's like a bunch of duplicates or what the actual deal is. Yeah, so there's a bunch of duplicates here. I think what I should be doing is something that stores this information. I think it's gonna be cache. Let's go ahead and try that. Feels still too slow. Okay, let me go ahead and just see if this up to here is fine. The time limit exceeded is within the algorithm or within the just calculating prime factors here. Okay, so it's getting the prime counts pretty quickly. Okay, so getting the prime counts pretty quickly. Then and it can't be taking that long to sort. I wonder. I wonder if you could do. How big is K? K is Okay. K is a huge number. I was thinking K would be much smaller. So maybe it is that one person suggested a monotonic thing. So if it is a monotonic thing, then for each number, yeah, so rather than do one multiplication at a time, you're it's monotonic going to be a single pass through this thing. It's a single pass through this thing. Single pass. Yeah, this is not even like a heap of, or not a heap where you keep track of the top k values. Keep track of top k values. So if you do a single pass here, then you can go through for every high value that you see, you extend it. For each high value that you see, you can try to extend it to as far for each value that you see, you extend it as far right as possible, and then you extend it as far left as possible. That doesn't really work. Does extending it as far left as possible, is that just the non-extension of the far right as possible? So for instance, if you go through it monotonically, go 1, then you go, then 1 can't extend right, so you're at 7, and 7 can extend as far right as far left as the earliest thing in your stack, and then you go 11, and 11 can go to 1, 5, and onwards. So it is it 1, 7, 11. Okay, so you keep a stack, monotonic stack, and then at the very keep a monotonic stack where each element extends as right as possible. How do you know how far it extends leftwards though? Oh gosh. What is the value of k? Is it like a million? Oh, k can be really large. K can be up to a million elements. So if k can be a million elements, you just can't do that. You can't multiply a million times. You actually have to do like exponentiation to quickly do those multiplications. So you quickly calculate how many times you should be multiplying. So if you did one pass where you extend it to the right as much as possible, and then you do another pass where you extend it to the left as much as possible, and then I don't know, you do another pass to figure out what the total amount of extensions is for each element. And that should be pretty quick. And then you can do a sort. No. Yeah. You can do a sort at that point. So is that, how is that I guess that is faster because you're doing one pass for each. Okay. So I guess the person that said the monotonic stuff was right. Okay, I think this is just not what I want to do right now. So this can be a monotonic. What is the tabbing here? Monotonic. Stacked track how far left and right each, how far left and right a value extends. Is that monotonic? Sure. I don't know. Right is going to be an array for each value in my nums. Or rightmost is going to be that for each index in the range of nums. For each index in the range of nums. Yeah. I'm going to say the value is equal to the nums at this index. If this value is bigger than, if this value is, no, if the score of this value, say the score is equal to my prime counts at this index, and then it's going to be while this score is bigger than the rightmost. I'm not sure if this is mono, the pop element of mono, and the mono needs to keep track of both the value and the index. So mono should start with the original value, which is the first value in nums, and the value and the index. The prime score. No, I'm keeping track of just where the prime score ends. So I don't need to know about the nums. So it'd be the prime score or prime counts of 0 and index 0. So I don't really care about the value actually. If the score is bigger than the current rightmost score, so mono of -1, while mono exists. Mono and actually I guess this should start with just an empty stack. While mono and the top of mono, the score of it, which is the 0th element, while this is bigger than that, then pop it off. Mono. I need to do some other stuff here. Keep track of ending of this element. And then it's going to be just something like mono.append the current score and the current index. Okay, so to keep track of the rightmost using a one pass, is going to be you always add the score and index, and that always happens because every element could end rightmost at its current position, and then whenever you see something that is bigger than it has a bigger prime score than something that is before it, then the thing before it ended. So I'm going to say here the thing before it ended. So rightmost, this is going to be an array, and let's say it's going to be -1 times the length of n. So rightmost times n. Score greater than mono. So when do you calculate the rightmost? So whenever you pop something off, then you know that the rightmost value of that element is this spot. So say I don't really care about the previous score, just care about the previous index. And that previous element's index, the rightmost value of it, is going to be equal to, no, so previous index the rightmost of that previous index is going to be this spot. And then yeah, rightmost value of it is going to be this spot. So everything. Okay, I think that is correct. Now, is this always going to store rightmost for everything? Maybe it should be this spot -1 if I do inclusive or non-inclusive. This is, I guess, non-inclusive. And at the very end, there should be inside the mono stack all the elements whereby they still extend to the end. So while there's mono stack and pop the element off, and the rightmost of this index is equal to n. Go and print mono. For each range of nums. Okay, so the mono. Oh, print the rightmost. So this is not doing it correctly. Well, yeah, it's not doing it correctly here. So evaluate. Alright, so after each of these, I'm going to just go ahead and print out what the mono stack is. Okay. Test cases, remove this test case. So 8 goes to, so it's 8 is the first prime. I don't think I actually called prime counts, did I? When did I do prime counts? Okay, I did do prime counts here. Okay. So print the prime counts here. Okay, so the prime counts is 1, 1, 1, 1. Okay, so I guess that is all 5s. Alright, prime counts here is 1, 2, 2, 2, 2, 2. So the first one extends to the first one score is 1, index is 0. That's after the first pass. Okay, after the second pass, it's going to be, yeah, it's going to be 2, 1. Okay, actually this is right. So this is 1, it extends to 1, and all these ones extend to the end. So 0, 1, 2, 3, 4, 5, and ending with 6, okay. This one is 3, 3, 4, 4, so this one extends to so as long as it's bigger than or equal to, so 0, 1, 2. Yeah, so it'd be 2, 2, 4, 4. What is this? And then this last one extends to 1. This one all extends all the way to the end. This one only extends to itself. This one extends to the end. Okay. So now I'll have another stack for the leftmost. For each index in the range of n. For each index in the range from n minus 1 to -1 decrementing. Score is equal to the prime counts at this index. And I'll just do another mono. This one's going to be, yeah, another mono stack. Okay, while mono and score is greater than, or is strictly, it needs to be, if you extend leftwards, the score could be, you pop it off if it's equal to, no, right? So if you're doing rightwards, you need to pop off when it's equal to, while mono and score, okay, when you're doing rightwards, if it's a equal, then it stops. If you're staying leftwards, you're extending leftwards. The logic here is you're extending rightwards. If you see a score that is greater than you, then that has to end the rightmost. Okay. If you extend it leftwards, shouldn't that also be greater than? If you see a score that's greater than, then you should stop extending it leftwards. Seems like this logic should be different. So this is going to be the previous index, and then leftmost of this previous index is equal to this index, and then mono.append score index. This is just let me see this here. I feel like I'm missing some logic here. And leftmost of this index is going to equal 0. Print the leftmost. It feels wrong to use the exact same logic. Or pretty much the same logic. Alright, let's just see how this goes. Alright, so 8 can go left to 0. 3 should only go left up to 8. Right, so yeah, this should be greater than greater than or equal to, while mono and the score, this score is less than, no, greater than or equal to. Okay. 8, 0, 3. 3 should also, the leftmost 3 should go is just 1. 9. So this is off by 1. Let's see how much this is off by. 0. 12 should go to 0 as well. 14 should go to so how far something extends to the right? How far something extends to the right? I wonder if I can do the reverse logic. So how far something extends to the left should be, so maybe I don't need to actually calculate the right. So if 12 extends all the way to the end, 19 extends all the way to the right. So 14 extends all the way to the right. But then going from 14 to the left, for any subarray there's a unique prime score. So you can't have the same subarray used as different left and right sides. So if I can calculate where it extends to the right, then shouldn't I be able to say that that right can only extend as most, or at least to the current spot? Okay, there has to be some prime score. You're starting with, say, 18. 18 has a prime score of 2. So sure, left. So you pop down to the stack. And then you go to 10. 10 has a prime score of 2 as well. And because 10 has a prime score that is bigger than or equal to 18, then it should pop off the 18. So this is actually right. So 18, 0, 1, 2, 3, 4. So 18 extends to the left as 4. So not inclusive of the left here. Or I could do inclusive of the left and say this goes to, let's go to index plus 1, current index plus 1. Okay, so what's the thing here? So 18 extends to just itself, 5. That extends to itself 4, 3, 4, 3, 2, and this one extends all the way to 0. This one extends to 0. Yeah. Okay, I think that's actually right. Okay. So you have the rightmost extension of a given index, you have your leftmost extension of given index, and I'm gonna go and calculate how many for each index. Total windows or total subarrays for each index. For each index in the range of n, the total for this index, so the windows for this index is equal to the index is going to be the rightmost index minus this index times the leftmost index times leftmost. So index minus leftmost this index. So if you have on the right side 1 and you have on the left side 2, then you do 2 times 1. Rightmost is not inclusive, so this is the correct one. Leftmost is inclusive, so you need to do +1. And then I'm going to go ahead and just print the number of windows. One times n. Okay, so the number of windows with 8 is just 1. With 3 is just 1. With 9 should be bigger than 1. Nine should have like 1, 2, 3. Oh, okay, the number of windows with 8 is 5. 5, 4, 3, 2, 1, that's right. And the number of windows with 19 is 1. The number of windows with 12 is going to be 1, 2, 3, 4, 5, then times by 2, so 10. 14 is 1, 2, 3, 4. 6 is 3, 10 is 2, 8 is 2, 18 is 1. This one was 3, 3, 4, 4, so it's going to be 1, 2, 2, and then just 1, and then 1, 2 times 2 times 3, so 6. And then this is just 1. Okay, so that's the correct number of windows. And then just go through the actual thing. Go through the sorted biggest windows, biggest size elements. So So I think for index value in, if I do sorted enumerate the nums array, let's see. So what I care about is for each value what the size of the window is, and for each value the size of the window. So say array is equal to, for each index in range, n array.append nums at this index and the windows at this index, and then sort that, reverse. Oh, array.sort. And then for each, say I have a count, while, actually, is it while here? Answer is equal to 1, while count is less than k. So index is equal to 0. Answer, let's see, most is going to be, it can be the maximum, the smaller of the two. The minimum of k minus count, and how much is actually there. So this can be the array at this index, the size of the window, and then answer is going to be, count is going to be plus equals this most, and answer is equal to answer times the value here. Okay, so we'll say value and the windows that has, the size that it can have is going to be equal to array at this index. For forget index increment, the count can be what's missing or this up to the size. So if the size is smaller than what's missing, then you take the size. Yeah. And then count increments by how much you can, and answer times the value to the power of the most mod, and return the answer. All right, that worked. Output limit exceeded. Fair enough. Fair enough. Turn off some of my prints. Turn off this print. No, it's going too slow. Yeah, it's going too slow. Okay, so let's see if it gets to here. Print the array and then return -1. Should get to here pretty quickly. Okay, so it got there pretty quickly. Interesting. So there's a bunch of numbers that are duplicates. So what I could do is, rather than doing a window, I could use a default dictionary for this. The values themselves are not that many, right? 10,000. So I could use a default dictionary to combine some of these values, and then I sort by these by the keys. So Windows. So I could say Windows is a default dictionary of integers. And then rather than saying Windows at this index, I'm just keeping track of the score. So Windows of this index increments. No, sorry. The sizing of the windows still need to keep track. I think maybe a dictionary here is actually fine. Score map is going to be a dictionary. So for each index, the score, the value, actually this is the value map. So this is going to track map value to how many windows it can create, how many subarrays. So the value is going to be equal to the nums at this index. The number of windows is going to be, the size is going to be this jazz. And then the value map, yeah, it's going to be default dictionary. Value map for this value plus equals this size. Guess this, whatever. And then rather than doing this, the array is going to be sorted of the value map. No, the sorted of my Actually, I'm just going to sort my original nums. And then and then just this same code here, while count is 0, answer is 1, index is 0. Do I need to worry about index? Okay, I think count and answer is enough for each index in the range of n. The value is nums at this index. The size is going to be equal to the most you can do is going to be the min of k minus the count, and actually the size here is going to be how much things I have in value map for this value. Most is size, and then count plus equals most, answer equals answer times value to the power of the most, mod, and then if answer is if count is equal to k, then return answer. Value map. Oh no, it's still too slow. It's still too slow. Really? Really? Okay, so let's go ahead and print out the number of windows and print the value map. Does it get to that point? Okay, it gets there pretty quickly. And does it print the value map? Oh wait, it should be nums.sort first equals true. Okay, so 46,000 was the largest. No, it's not. 46,000 was okay, actually let's go ahead and try that one more time. So it's printing these things and it's returning -1. Wait, why is it returning -1? Count plus equals most. Oh, it's returning -1 because of this thing, right? Alright, so it doesn't work for this one, but if I do the other test cases just to make sure that it works for those. Okay, it works for those pretty quickly. Alright, so let's go ahead and print the at the value maps. So it gets to here fine. Gets to print out the value maps fine. Why would it be the repeated multiplication? So if you go through for each value in your nums array, oh, wait, does that even work? So for each value in your nums array, this should be for each value in your value map, where the value map is sorted. So 1 is 2, 7 is 8, 8 is 11 is 3, 1, 2, 3, 7 is 1, 1, 2, 3, 4, 8, 5 is 2. 5 shouldn't be 2, should it? 5 is, oh yeah, 5 is, yeah, 5 is 2. So your answer should be wrong for some of these, I think. It's not for every value in your nums array, it should be for every value in your value map. I think this should be array equals sorted of the map of nums. Reverse is true. Reverse equals true. And you should be going through your array for every value in the array. Get the size of that value. Okay, I think that's slightly more correct. Not sure why it didn't give an error before. Array sorted of list of the maps of nums. Oops, list. Can you do sorted of the set of nums? Okay. Still takes too long. Do. Okay, so why is it going to take too long? Why would it take too long? So let's do a quick check here. Print the for each value in array, print that value and the value map value. So 100,000, there's one, there's 3 of those, 1 of those, 16 of those. All unique. All unique. So do you not need to multiply them? Value times answer times value to the power of most. Is it an issue? So for each value, you're multiplying it to the answer. That's a million values. The minimum is going to be, okay. Oh, why is it so slow? Is there a faster multiplication than this? Could it be that I should be multiplying it? Oh. Struggle of the last 7. So you have your largest values. Doesn't take long to figure that out. You have how many times you need to multiply that value by. Doesn't take that long to figure that out. But then the multiplication is too slow. But don't you need to multiply in order to figure out what the answer would be? I mean, that's a huge number. That's 7 million with 700,000 multiplications. 700,000 multiplications. I guess that's a lot of work. How do you shortcut that? Shortcut that multiplication. The value to the power of most. Is that too big a number? I can even get slower when you have big numbers when you multiply them. Oh my gosh. 99,000. 99,000. Choose multiply your score by X. Okay, what is the first hint here? Calculate nums I by factoring in. Calculate nums I prime score by factoring in 0 square root by factoring an O of square root of nums of I time. Are my prime factors going too slow? Can't imagine it being going too slow here. Okay, hint 2. For each nums I, find the nearest index I on the left and right. If none is found, set similarly right. Okay. Use a monotone tax to compute right of I and left of I. That's fine. For each index I in the range of left I plus 1, then the maximum SI is the maximum value in the range left to right. This particular the variable will be chosen. Sure. Loop over all elements of nums by non-increasing prime score. Each element will be chosen min. Loop over all elements by non-increasing prime score. Sure. Use fast exponentiation to quickly calculate a to the power b mod c. What is fast exponentiation? With these uh, so answer times what, PAL of value to the most. Often used. Here we compute the half power of optimization. We're computing the half power of optimization method. Squared. Results. Okay. Okay. exponentiation to calculate a to the power b mod c. If the power is mod 2 is not even, if it's odd, then the result is equal to times the value. So you're doing half the power, and then you do multiplication of the result. I don't see how that is all that much faster, but okay. If the power mod 2, if the power is odd. Okay, I guess maybe I can do mod here. Leftmost, rightmost. So optimize value and power and most. What do I do on here? Alright, remove the -1 return here. Not be going that slowly. Time limit exceeded. Stop the prints. Actually, let's go remove the test case. Alright, and remove the prints. Add back in the test case. See if this optimize thing here. Fast exponentiation. Time limit still exceeded. Fuck. Fast exponentiation to calculate a to the power b mod c. Loop over non-increasing for each element chosen between the min of ranges. Okay. I'm just stuck with the fast exponentiation. Fast exponentiation function. Fast exponentiation function. Seasonal. If I'm using math.pow. Initiation for loop. How do I know how to? Yes, it has. Time complexity. Fast Python code that calls the first calls pow, then applies the modular operator. Pow ABP. Using direct fast method to compute. Oh, there's a modulo, okay. There's just a pow value most mod. I guess an extra mod is not going to hurt. Are you serious? So stupid. That's just so stupid. The fucking power function. Alright, whatever. Okay. Let's tidy this up. Everything here has to go. Spent like, what, 30 minutes on figuring out how to call power? Jesus Christ. I don't need that. I need that. Do need that. Alright, modulo prime counts. I guess I should call this prime score. Prime counts. Prime scores. Replace all. Okay, so you have each value, you calculate your prime scores, and then you figure out how far for each value extends left and right, dominating its neighbors. So rightmost is going to be that. And then I wonder if I should have been able to calculate the leftmost based on that as well. But whatever. Second pass, do the leftmost. And then slight optimization to calculate how often something occurs, some value occurs, the total size of all the windows. So the value map is the dictionary. I don't think I need windows actually. Yeah, I don't think I need windows. So for each value, look at the size of the window for this index in the leftmost and rightmost arrays and increment this value map size. Array sort, go through each element and largest to smallest. Go through each element, largest to smallest. Okay. And then for I wonder if I could no, I think this is fine. For every value in the array, look at the number of things for that value. Find at most how much you can take. Take that, add it to the answer, and then finish. Okay. Alright, I think that still should work. Should be slightly faster without creating that one array. Alright, whatever. 75% is good enough for me. Alright, so summary. This is going to be determine how create array to create corresponding prime score array for each value get its prime score, get its number of prime factors. And then secondly, you want to determine how far each value extends left and right as the biggest prime score of its subarray. And then calculate the total number of subarrays using size is equal to basically right extension times left extension. And then from there, go through the largest values to smallest, and include its number of subarrays into k, stopping at k. Also, last but not least, must use PAL base exponent mod to efficiently calculate. That last part was the killer. Time complexity, this is O of n, I think. O of n to determine the windows. And also this is going to be the O of the number of values, O of k, I guess, for calculation, because you could do most like k calculations here. If at worst each value was unique and each window was with size 1. So I don't know, O of max of nk. base complexity, this is going to be, there was a bunch of value mapping stuff, so it was like O of n for extra arrays to track stuff, especially the monotonic. Monotonic. Is that how you spell monotonic? Monotonic. Yeah. Monotonic stacks. Okay. Wow, that was brutal.